Hello. I'll do some problems here for section 2.3. This is very similar to 2.2, so here we go. We do have to think about complex numbers. Let's take a look here at number, number 13. Okay, so in this one what we're doing is we want to solve this differential equation, and we'll see that this is a third order differential equation. So what we do is we look for the characteristic equation, which is obtained by looking at the differential equation. Then you obtain the characteristic equation essentially by just rewriting the third derivatives as powers, and similar with the second derivative and the first derivative. Then we factor this. This is not an immediate thing. If you would use long division, or you can use the rational root theorem to factor this polynomial, so that you get r times the quantity 3r plus 2 times 3r plus 2 equals 0. And you notice that we have a repeated root. So then by the theorem 2 in our book, we see that the general solution of this equation is of the form y of x is c1 times e to the 0x plus c2 times e to the minus 2/3 x plus c3 times x times e to the minus 2/3 x. This is illustrated right here. Okay, I'm going to do number 30. Number 30, a similar type of a calculation here. We have a fourth order homogeneous linear differential equation. So we write down its characteristic polynomial. Okay, and then we factor this. Here again we could use the rational root theorem, trial and error, or somehow we factor this using our algebraic techniques that we've learned to come up with this factorization of the characteristic polynomial. And now here, notice the thing that's different is we have this root right here. Now, I should say factor right here. Now there's a nice explanation of what happens when we have complex roots. Essentially, if you just follow through the algebra, and what you notice is that when you have a complex root, as we do there, we have two complex roots. So they are complex conjugates. And so we see that we get the root r as minus I times the square root of 3, and also r equals I times the square root of 3. So then using the conclusions of theorem 2 and 3, we see that the general solution to this fourth order homogeneous differential equation, linear, is given right here, where by essentially de Mauvier's theorem, we have to introduce the exponentials of complex with complex numbers, and we basically arrive at this conclusion that the general solution is c1 times e to the minus x, c2 times e to the 2x plus c3 times the cosine of the square root of 3x plus c4 times the sine of the square root of 3x. Okay, number 42. Here we are going to go the other way. We're given a solution to a differential equation, which is right here. And what we want to do now is we want to try to find a differential equation that has this as its general solution. So we interpret theorems 2 and 3 in reverse and sort of search out the differential equation. And we notice that the conclusion of the theorem 3 would indicate that we have a complex roots plus or minus I, plus or minus 2i with multiplicity 3. So therefore, what that translates to is that this would be our characteristic polynomial, which is this right here. This is our characteristic polynomial. So expanding this using multiplication, we find that that is equal to this characteristic polynomial. So reinterpreting this back into exhibiting a differential equation that gives us this characteristic polynomial, we see that the one solution might be this differential equation. Actually, this differential equation works, or any constant multiple of this differential equation will also work. So, all right, here we have it. Now, number 46, we have this very unusual situation where, and we won't be encountering this too often in the future, but here we have a differential equation where we're allowing for complex coefficients. We have a coefficient of y prime here being minus I. So what we do is we follow the same sort of technique. The characteristic equation is given here, r squared minus ir plus 6 is 0. Factoring the characteristic polynomial gives us the factorization r minus 3i times r plus 2i. You can either do that by inspection or by using the quadratic formula, whichever you prefer. Yielding the roots r equals 3i or r equals minus 2i. And then the same theory basically carries over, and we have this general solution. So there's 2.3, some examples of problems that are analogous to your homework. I hope this is helpful. If you have any difficulty with the material in there, it's a little bit cumbersome when you go through the, when you read the explanation on how the complex numbers come into play. But if you have any questions, please feel free to contact me. Thank you.